Alright, welcome back everybody. In this video we're going to look at examples 3 and 4 from the Revisiting Particle Motion lesson. We'll start here with example 3, which is free response question number 3 from the 2004 AP Calculus AB exam Form B. So this is a calculator free response question. I hope nobody gets nauseous as we scroll back and forth throughout this. So if we look at the lead-in, a test plane flies in a straight line with positive velocity, v of t, in miles per minute at time t minutes, where v is a differentiable function of t. Selected values of velocity are shown in the table above. Alright. Part A. Use a midpoint Riemann sum with 4 subintervals of equal length and values from the table to approximate the integral from 0 to 40 of v of t. Show the computations that lead to your answer. Using correct units, explain the meaning of integral from 0 to 40 of v of t in terms of the plane's flight. Alright, so first we want to approximate the integral from 0 to 40, and we're told to use 4 subintervals of equal length and a midpoint Riemann sum. So since the entire time interval is from 0 to 40, subdividing that into 4 intervals, we'll have the interval from 0 to 10, 10 to 20, 20 to 30, and 30 to 40. Excuse me. And we're going to base the heights of our rectangles for this Riemann sum off of the value at the midpoint in each of those intervals. So we're taking the height at 5, 15, 25, and 35. Alright, so to approximate this value, we're going to have our width of 10 times the height of each of the rectangles, and we can just factor the 10 out in front since it's a uniform width. We've got 9.2 plus 7.0 plus 2.4 plus 4.3, and now we'll do the calculations. That's 10 times 16.2, 18.6, 22.9. And so that's 229 miles the test plane would fly over that time period. Alright, using correct units, explain the meaning of this integral. Well, since it's the integral from 0 to 40 of v of t, and v of t is always positive, this is going to be the distance traveled. So the integral from 0 to 40 of v of t represents the distance traveled by the test plane in miles. Over the 40 minutes. 0 is less than or equal to t, less than or equal to 40. Alright, part B. Based on the values in the table, what is the smallest number of instances at which the acceleration of the plane could equal 0 on the open interval from 0 to 40? So in order for the acceleration of the plane to equal 0, we're looking for places where the change in velocity goes from being positive to negative or negative to positive. And so looking at this, we've got the velocity increasing, 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 and then it starts to decrease here. So there's one place. And then we see that it decreases, decreases, and then it starts to increase again. And so there are two instances and as far as justification, what we're looking at is we're looking at there are two places, come on stylus, there are two places where change in velocity which is acceleration, changes sign. Alright, part C. The function f defined by f of t equals 6 plus cosine of t over 10 plus 3 sine of quantity 7t over 40 is used to model the velocity. According to this model, what is the acceleration of the plane at t equals 23? So all we're looking for in part C, and remember now this is a calculator section, all we're looking for here is f prime of 23. And since this is a calculator section, I'm just going to go ahead and use the numerical derivative of 6 plus cosine of t over 10 plus 3 sine of 7t over 40 at x and at 23. And so we get negative 0.408. Okay, now since this is acceleration, and the velocity is represented in miles per minute, this is going to be in miles per minute squared. Alright, in part D, according to the model, f, given in part C, what's the average velocity of the plane in miles per minute over the time interval? And so this is just going to be 1 over 40 minus 0 times the integral from 0 to 40 of the velocity function. That's how we're going to find average velocity. And so again, I turn to my calculator. I'm going to use the numerical integral this time. And the numerical integral of the velocity function from 0 to 40, and then I'm going to take that value and divide it by 40. Oops. Looks like I typed something in wrong here. Integral, close the parentheses. Oh, I missed the 0. From 0 to 40. Now I should be good. Alright, that's 5.916. And since it's average velocity, this is miles per minute, although it told us that in the question, so we don't really need to re-illustrate that. Alright, that's the end of that example. Let's go on to the last example here. The graph below represents the velocity of a toy car traveling along a straight track for time 0 to 40. At time t equals 0, the car is at position 0 on the track. Find a of 18. So a of 18 is the acceleration at time 18, and time 18 is over here. This is a graph of velocity, and so a of 18 is going to be the slope of this line segment that we're on the graph at time 18, because acceleration is the derivative of velocity. So we're going to have 45 minus negative 45 over 12 minus 20. So we've got 90 over negative 8. So this is going to be negative 11.25. And what are my units here? I have no units, so I don't need any units in my answer. Alright. Part B, where is the toy car at time 20? Okay, so in order to find where the toy car is at time 20, since we're working from a velocity graph, we need the displacement plus where it was at time 0. At time 0, it was at position 0, so we don't need to worry about that. So all we need to do to figure out where the car is at time 20 is we need to approximate, or rather find, the integral from 0 to 20 of the velocity function. And so in order to do that, we're going to look at this velocity function, and we need all of this area counted as positive, and all of this area counted as negative. So let's see, what's the best way to do this? This is a trapezoid that's 6 units wide here, and 45 units tall. And I need to know where this point is. This point is the point 16, 0, which I can tell from the slope of the graph, and the fact that it goes from 45 to negative 45 from time 12 to time 20 tells us that it's at 0 at time 16. So the width of this is 16. So I can find the area of that trapezoid. And then this width is 4, and the height is 45. And that's counted as negative. So I've got a trapezoid where the bases are 16 and 6. So I take the average of those bases times the height and subtract away the area of this rectangle, or this triangle, pardon me, which is 1/2 times 4 times 45. And then I go ahead and do those calculations. 11 times 45 minus 2 times 45. That's 9 times 45, which is 405. What's the total distance traveled by the toy car over the 40 seconds? In order to do that, we now need to calculate all of the area as positive area. So we've got the trapezoid from the start, plus the triangle that we just calculated, plus the remaining areas, which, let's see what else I've got. I've got a trapezoid right here with a width of 10 and bases of 45 and 15. So we'll add that area on. 45 plus 15 over 2 times 10. And that takes care of this area. And then I have this little triangle, which is how many units wide? Let's see, where does this cross? If it goes from negative 15 to 35, that means it crosses 3/10 of the way. So this crosses at 33, 0. And so we've got a triangle that's 3 by 15 is next. And then we've got one last triangle up above here, which is 7 units wide and 35 units tall. And then we'll go ahead and add all those areas together. This is 495, this is 90, this is, let's see, 30 times 10 is 300. This is 45 over 2, and this is 245 over 2. Combine these two together, gives you 290 over 2, which is 145. So 495 plus 90 plus 300 plus 145, that's 640, 730. 1,030 units is the total distance traveled by the toy car. Alright, that's the end of the examples from the Revisiting Particle Motion lesson. See you guys next time. Have a great rest of your day.